Good morning, everybody. My name is David Gigonye. I'm with the Itasca Consulting Group in Minneapolis. Welcome to our webinar today on the overview of slope stability analysis methods presented by Loren Lorig. Before we get started, just a couple of points. If you have a question, please type it into the question dialog in the GoToWebinar control panel. And then what we'll do is, if we have some time at the end, we will address the questions. If we run out of time, then we will simply follow up with the questions and include them with the presentation that we'll distribute within a week on our website. A little bit of background about Loren. Loren first joined Itasca in 1985. He was the general manager of our office in Chile for about 15 years. And he was the CEO for about 8 years of Itasca International. He's currently a senior principal geotechnical consultant, and he has worked as a consultant at most of the large open pits worldwide. So with that, I will pass it along to you, Loren.
Thanks very much, David, and thanks to everybody who's joined in. This is a topic that I'm very passionate and interested in presenting and have worked at for most of my professional life. So it's really glad I'm really glad to be able to share this with you. The topics for today are pretty broad, and you can see them here. We're going to start off with a couple of key references, and we'll talk about all kinds of different methods from the oldest to the newest. We'll talk a little bit about everybody's favorite topic, comparing limit equilibrium and numerical methods. I'll try and answer some important questions at the end and then just provide some final thoughts. I'm not going to talk about a lot of things that are important to slope stability. As you see on the right there, things like rock mass characterization, strength estimations, hydrogeology, rockfall, and runout. All of these things are very, very important, but in order to keep this to a manageable length of about 1 hour, we're going to have to just leave those alone. So 2 really key references, if you're only going to have a couple of books in your library or on your computer, these are the 2 I would suggest. On the left, the guidelines for open pit slope design put together by the Large Open Pit Project. Chapter 10 in that particular book talks about all of the different slope stability design methods. And then a more civil engineering oriented book on the right from Wiley and Ma is really a follow-on from the 3rd edition of Hook and Bray's classic text on rock slope engineering. So these are 2 very good references. Pretty sure they're available in electronic form for purchase. But as I said, if you're only going to have 2 things, these would be the 2 to have. So let's start with physical models, and physical models are the oldest type of slope stability models that we have. And they were used mainly before computers, but they still are used in some places now, and I'll show you where those are. So one of the first ones was called the base friction model that was developed by Dick Goodman at the University of California. And he used this to simulate gravity by rotating this belt below a system of blocks, and the speed of the belt then represented gravity. Interestingly enough, we'll show an example from this that Peter Kundal developed one of his first programs with to provide a calibration, or not a representation of the this very same physical model. And physical models were quite in vogue in the early 70s and late 60s, particularly at Imperial College, where Peter Kundal and Nick Barton were students under Everett Hook. This is an example of a physical model that Nick Barton used for his PhD, and you can see here that you simulate the slope with these blocks, and you just excavate the slope as you would in any other method by removing material. Methods which are still used today are centrifuge tests, and this is an example from 1997 of a synthetic material with multiple parallel joints. And again, we'll look at the results of this test in a numerical model later on in the presentation. But that's about it for physical models. Very expensive, very hard to do. And fortunately, computers came along. But in between, there were analytical methods for simple failure mechanisms, planar failures, wedge failures, circular failures, toppling failures, and there were relations and equations developed to calculate safety factor for various simple instabilities. And this is probably the simplest. It's a planar sliding example, but there is a tension crack, a vertical tension crack at the back, and you can put water in it, and you can see the equations there used to calculate the safety factor for that particular slope. And you can take those equations, if you like, and you can develop design charts, such as shown at the bottom here, that relate the sliding surface angle and its frictional properties in terms of slope height and slope angle. And this is the most common way to present results for slope stability are in these charts relating slope angle and slope height. And we'll see that again when we come to the empirical methods. But this is just for a simple planar sliding case. A little bit more complex is when we have two sliding surfaces that form a wedge. And again, analytical expressions are available to compute those safety factors. And these things are all coded into programs like SWedge if you don't want to do your own calculations. And then there are circular failure charts for different water conditions, as shown here in the text from Hook and Bray in 1981. Different water conditions, assumptions all the way from dry to fully saturated. And then a series of graphs were developed that allowed people to calculate safety factors for any of those assumed water conditions. There were, I think, 5 different charts. And to do those analyses, you simply calculated the cohesion and the weight and the friction angle, and you then followed a line down to a particular value of the tangent of the friction angle divided by the safety factor, and then you went over and for different angles, then you could find out the friction angle. You could find out the safety factor knowing the friction angle. So pretty straightforward for simple slope stability. Then the last one is block toppling, a little bit more complex, and this particular analytical solution tells us which blocks will topple, which blocks will slide, and which blocks are stable. And again, there are equations for each of the blocks shown here, and it's quite a bit more complex to calculate this, and there are examples of how to do this in, for example, Wiley and Ma, the the second reference text that I showed you at the start. Then empirical methods are experiential type representations of slope stability, where people have collected data about slopes that have failed, slopes that are stable. And here are 4 of them that I'm aware of. There probably are. These are probably the best known, starting with Hook and Bray in 1981, Haynes and Peter Tuberga in 1991, Yanni Schoberg in 2001, and Trevor Carter and Carlos Carranza Torres in 2019. Interestingly enough, these empirical methods seem to pop up about every 10 years. Looks like we missed 2011, but maybe there's one around. But they all are representations of slope instability. This is the first one by Hook and Bray. And again, we have the slope angle on the horizontal axis, the slope height on the vertical axis. And interestingly enough, this sort of tells us also about what slope heights were important in 1981. So 40 years ago, most slopes were less than 300 meters high. There's no data in this chart much beyond 250 meters of height. So these charts typically show slopes that have failed, and in this case, the red dots, and stable slopes, in this case, the open green dots. And then there is, in this particular case, curves fitted through the data to represent different safety factors. One of the characteristics of all empirical methods, not just slope stability, is that they're not perfect. We have points out here which are stable, which we might think should be unstable, and we have the opposite. We have some points over here which are unstable, which should have a safety factor of 1.6. And this is typical of geologic materials. We don't know their properties perfectly. We don't ever know the distributions of various materials, water, and so on. And so when you attempt to put these curves together, you naturally end up with some points on either side of the line. If somebody shows you a line where all the points are on one side and all the stable points are on the other side, they probably fudged the data. So another one in 1991, this one uses the Laubcher modified rock mass rating, the RMR. And it's a simple matter of then looking at the RMR, looking at the slope angle, and figuring out what sort of slope height you can achieve with that. But you could also cast this in exactly the same form as the previous chart. Yanni Schoberg in 2001 looked at lots of examples, put together charts. There's more than one chart, but this is typical of what he did. And the thing that he did differently than Hook and previous charts was to separate it by rock classes. And so you can see then the squares are class R4 and the diamonds are class R3, and you can see sort of where they plot on this chart. And the last one is a fairly recent one, much more data, and it's characterized in terms of the Hook-Brown parameter M sub B, as shown over here on the right. For this work, the authors assumed a d-value of 0.2 in putting together this chart. So you can look on here and find curves that fit your particular rock mass and look at whether they are predicted to be stable or unstable. Interestingly enough, now in 2019, we're starting to look at much higher slopes, several values over 1,000 meters. I should say they also included natural slopes in here. These are not all mined slopes. Some of them are natural, and that's how we end up with some of these points way over here near vertical for more than a kilometer. Those are from natural slopes rather than mined slopes. Okay, then moving on to limit equilibrium. Going to talk a little bit about the basics of the method, compare some different limit equilibrium methods, and talk a little bit about the missing physics. But I've listed down here, if you're really interested in finding out more about limit equilibrium in particular, this is one of the best references, the one by Duncan and Wright. So limit equilibriums methods tend to divide the slope into slices and then calculate forces acting on those slices that put all of the slices into equilibrium. And we can, as shown on the right, we can include water within the slope, which reduces in the base the shear resistance. But these are all put together in commercial software. You don't have to do any of this yourself unless you're really keen. And what we find is there are all kinds of methods. Most of them are listed over here, which you can use. They have different formulations for looking at the search algorithm, different algorithms for side forces and so on. But you can see here for a very simple slope, all of these methods produce safety factors which are essentially the same number except for the ordinary slip circle method. But all these other ones, these method of slices here, all produce essentially the same number within what we know about material properties. The literature that I've read suggests that Morgenstern Price is probably the most complete and accurate method. So if you're going to use limit equilibrium methods, try to use the Morgenstern Price one. But again, for simple methods, very similar answers. However, there is one thing that's very interesting and doesn't pop up very often because people don't either know about it or use it. So on the right-hand side here is kind of the traditional method where we have these vertical slices and we're calculating forces between slices and on the bases of the sliding surfaces. And in this particular example, you end up with a safety factor of 1.25 for this example. However, if you relax the algorithm and say, well, these slices don't necessarily have to be vertical, I can reformulate that and consider inclined slices, you get a completely different answer. And the reason for that is, and this is a safety factor of 1.05 compared to 1.25. And the reason is that in this particular geometry, very often you end up with an internal failure surface that is inclined, and you end up with an active block at the back and a passive block in front that typical limit equilibrium methods just cannot capture. And we're going to come back to this in a couple other cases to highlight just how important this internal deformation can be. And it is for this reason that a lot of limit equilibrium methods tend to overpredict stability if there is some mechanism for internal sliding and deformation. And of course, this has been extended into 3 dimensions now, following the same kind of logic, but obviously much more complex. And here's just an example of comparing on the left here a 3-dimensional slope limit equilibrium result, and the equivalent model in this case using a finite element model using the shear strength reduction method. And again, for this simple slope, very similar safety factors, 1.51 and 1.53. So these are some of the commercial limit equilibrium software that I was able to find the supplier. And one of the things that's interesting about this is some of these various companies are being bought and sold in recent times, but this is, I think, the most up-to-date list that I could find. So both 2D and 3D limit equilibrium methods. Now, let's talk about some of the missing physics in limit equilibrium. So first of all, we have to acknowledge limit equilibrium methods have been popular for a very, very long time due to their simplicity and ease of use, but they do have limitations. And we have to recognize that they're based purely on statics, usually summing moments and forces vertically and horizontally. But of course, there's nothing in here about deformations, about strains or displacements. And so it does not necessarily satisfy displacement compatibility. And it's this piece of missing physics that causes some of the difficulties in the limit equilibrium method. Another problem is the assumption that the vertical stress at the toe of each of the slices can be calculated by the weight of the material directly above it. And this chart on the left-hand side here compares the slice number in here and the normal stress from the limit equilibrium assumption, which is this sort of parabola-shaped blue dots, and the actual finite element distribution, which is much different. And the difference comes from the stresses acting particularly down here near the toe, and the toes are very important in slope stability, and having a difference between an idealized assumption and an actual normal stress causes some errors in the limit equilibrium. So this the developer of the GeoSlope program recognized this, and he said, well, one alternative is to just set aside the whole concept of using statics and move totally to a stress-strain-based approach. In other words, he said, use finite element software to get these stresses correct at the bottom of the slope, and then you'll be all set. Well, seems a bit odd. If you're going to go to the trouble of using a finite element software to predict the normal stresses, why not just use the finite element software to give you the whole solution? But of course, he's promoting limit equilibrium as a solution method. So, but interesting nonetheless. So let's then talk to the more traditional numerical methods, which we're probably more familiar with these days. Two types, finite element and finite difference, that have long histories, but maybe not as long as limit equilibrium. The finite elements were developed in the early 1960s at the University of California. And I didn't find an example of a slope stability model, but I did find this example of a dam. It's a two-dimensional analysis of a dam. And in 1960, this is the largest problem that could be solved. They couldn't include any more elements. This was it, and with the computers available at that time. So a simple 2D model with, I don't know how many elements are there, maybe 20. And that's all that could be done, but yet a lot of work was done. And of course, computers became much more powerful. About a decade later, Peter Kundal at Imperial College was working on slope stability problems and developed two finite difference models, a discontinuum model. So you can see on the right this block toppling model, which was the one that was being solved by the base friction model that I showed at the very beginning of this talk, and developed this model with rigid blocks, which eventually then became UDEC. At the same time, he also developed continuum models based on, again, finite difference principles, and those then went on to become FLAC and FLAC 3D. But these are some of the very earliest models. The commercial software that use these methods are shown here. The first, second, and last one are the finite element models in 2 and 3 dimensions, and then the Itasca models, the continuum models in the upper line, and then UDEC and 3DEC in the lower line. Just a little commercial message that FLAC slope is a two-dimensional method based on FLAC, but it is menu driven and very simple to use, and it's free. You can download this from the Itasca website and use it. In my work, I don't do many models anymore, but I do use FLAC slope because it is so easy to use. You can solve a good variety of problems and very intuitive. And so if you're inclined, maybe download that and play around with it a bit. And it gives you a very good feeling for how numerical models work if you're not familiar with them. Just a little bit about the differences between finite elements and finite differences. They both divide the model into zones or elements or whatever you want to call them, essentially areas or volumes. And then at the corners, we have nodes. So the nodes typically have information about displacements and maybe velocity. The spaces have information about stresses and material parameters. And then it's a question of how you solve this sort of mesh to get an answer. In the implicit method, which is the finite element method, you have a stiffness matrix that represents each of the elements in terms of its properties and its geometry, and those are expressed in terms of applied forces and displacements through a stiffness matrix. And then it's a simple matter of assembling those element stiffness matrices into a global matrix of elements. This happens to be for dynamic analysis, but it would look exactly the same for static analysis. You just have a large system of equations that has to be solved for each time step. And if there is any nonlinearity, you have to iterate within that to make sure everything satisfies all of the compatibilities of strain and displacement. So that on the right-hand side is finite elements. On the left-hand side, finite difference, an explicit formulation here, which is somewhat different. So we assume at one point that all the displacements are fixed, and we calculate forces acting on the corners of the elements, in this case, as forces through some constitutive relation, which can be nonlinear. And we assemble all those forces divided by the mass associated with each node to calculate the displacement through Newton's second law of motion. And you repeat this for as many cycles as required to achieve equilibrium or to demonstrate instability. The limitation of this particular method is one of not allowing the physical model to propagate faster than the wave speed in the solid. So this depends on the properties of the material. So typically these methods have fairly small time steps, but within each time step, all of the forces and stresses are satisfied. So each time step is a physically meaningful result. It may be on its way to equilibrium or instability, but it is representing the evolution in the path towards those conditions. So just to summarize that we can in specific cases show that the algebraic equations resulting from both finite elements and finite difference are identical. And particularly for elastic models, they give identical solution. The element stiffness matrix for the flat triangles or tetrahedrons are identical to those for finite elements. So there's no difference there. The real difference is in the solution scheme. Obviously, Itasca prefers the explicit method because it allows us to follow nonlinear material behavior in a more physically realistic way than the implicit methods do. And it also includes mixed discretization, which is probably the best formulation for plastic flow that there is. So just going on, leaving the traditional numerical methods behind, let's talk a little bit about some new numerical methods that have been developed and are being developed, because this is kind of a glimpse of the future. And there are three different ones that I'm aware of. Hybrid methods have been around for quite some time. And what they are these are methods that allow a transition from a continuum model to a discontinuum model due to internal fracturing within the model. So we can see here a couple of examples. This is this toppling model that we looked at previously. but there are stress concentrations that can occur at the toes of each of these blocks, which may cause these blocks to fracture and fail. And so this is a sort of evolution, if you like, of this slope where we start to see some fracturing. It continues and the slope fails due to a combination of deformation of the blocks and fracturing of the intact material. Here's another example similar to that. Again, some fracturing occurring at the toe of this slope and the eventual collapse of the slope. So there are a number of people working in this particular area. Most of the results that I have seen are limited to two-dimensional models. You very seldom see this in 3D, but I'm sure people are working on it. But it's very computationally intensive to do this. An alternative to this is something called the lattice method. And it's a slightly different scheme. It has an arrangement of nodes, which are these little dots or masses, and they're connected by springs with simple tensile and shear behavior in them. So you assemble this this model with these springs and these nodes, and you put very many of them because the equations for movement of these nodes is, again, Newton's second law of motion. The springs are very simple calculations, and you produce the fracturing behavior as these springs start to break. So it's similar to the way new fractures might form in a distinct element method, but it's much faster because it is a simpler representation of that. And of course, we can put in then sliding planes, pre-existing ones, and allow them to have characteristics of a joint. So we can assemble models which are very much realistic and a little bit more efficient than those hybrid models with finite elements and distinct elements. So it's quite different in many respects than the conventional approaches because of this lattice formulation, which are, as I said, put in a sort of quasi-random fashion, and they're connected by springs. We don't really have a continuum fracture criteria, but each of the springs has a tensile failure and a shear failure mode. And so the overall behavior then emerges as the constitutive relation of the material. So here, this particular lattice model that Itasca has developed is called slope model. And this is an example of the block toppling that we looked at previously as an analytic solution. And here, this is a slope model representation of that. You can see the joints here. You can see the movement, which is largest at the top. And you have three different conditions. We have blocks which are sliding. These four blocks here, which all have the same displacement, are sliding as one. These blocks up here, these four are stable. They're not moving at all. And these blocks are all toppling because they have larger displacements at the top than at the bottom. So these lattice models are capable of reproducing those kinds of behaviors. And if we go back to the example of the centrifuge physical model, we've compared that to slope model as well. The representation on the right are slope model results. the physical model is on the left, and you can see there's very good agreement about where this lower fracture surface forms in the physical model and how it's represented in the lattice model. And it's really quite remarkable how close that is. So the last model I want to talk about is called the material point method, and it's categorized as a meshless or mesh-free or continuum-based particle method. And it's kind of halfway between a continuum and a discontinuum. This is something that Itasca is currently developing, and here's just a little animation from one of the early models looking at this particular slope failure. And I said at the beginning we weren't going to talk about runout, but this particular type of model is very useful for looking at where slopes may end up when they fail. And obviously in open pits, that's an important consideration. So I want to go back now. That concludes the sort of overview of all the different methods, but one of the most controversial topics, I think, is the difference between limit equilibrium and numerical methods, and everybody has their favorite. And there have been many articles written and master's theses written devoted to this particular topic. Which one's better? What are the advantages? What are the disadvantages? You name it. So I just want to put a couple of things to rest. There are people that say, well, factor of safety is limited to limit equilibrium, and strength reduction factors or shear strength reduction methods are different. So they really are not. The equations are identical. In the limit equilibrium, we simply divide the cohesion and the friction by a safety factor. In the numerical model, we call it a strength reduction factor, and we reduce the properties by that. But the equations are identical. And again, it's just the method used to solve the system of equations or the method of slices that produces some of the difference. But the fundamental point is that factors of safety in limit equilibrium and shear strength reduction methods in numerical models should give similar results. And here's an example comparing a limit equilibrium model on the left and a numerical model from rock science on the right for this same problem, which has a water surface. It has benches in it. And the Morgenstern Price safety factor for this slope is 1.0. The numerical model is giving a safety factor of 0.97, so very close. And the difference probably comes about because of some slight differences in stresses at the toe and the shape of the failure surface. So we can go back to this chart that I showed previously and look at the comparison between factors of safety and shear strength reduction. And we can see that they're, again, very close. And for simple models like this 2D model shown here, the answers are going to be close. But they begin to diverge when we get more complex behavior. And one of those complexities is when we have internal deformation or we have internal shearing. And the classic example is the active-passive mechanism that occurs in some slopes. This is a particular real problem where there's a horizontal bedding plane, which is very weak, and failure back up through the rock mass, but there is some internal deformation. You can see it no matter what the assumptions are. Here, there are two assumptions. The upper one, the shear strength reduction method, is applied to everything, to the rock mass, to the sliding surface. And you can see the result there. It ends up with safety factor of 1.55. But if you exclude the sliding surface from the calculation of shear strength reduction, perhaps this is already sitting at its residual strength and it cannot go down anymore, then you get a different picture. You get a much higher safety factor. And in this particular example, the correspondence with the actual locations of deformed surfaces are much better. So 2 points relate to this. One is that very often internal deformation is important, and this could either be rock mass or we could have inclined structures which are dipping at what I will call a toppling orientation, but maybe they're few and far between, so we don't see toppling, but we can see internal deformation. And the second point is that with the shear strength reduction method and numerical methods, we can choose to not reduce properties of various components if we want to. Maybe we think that they are already at their residual strength and can't get any lower, or we may just want to find out a partial safety factor due to other components, and this is all possible with numerical methods. So just to summarize some of the advantages of using the numerical methods to calculate safety factor or shear strength reduction factor. First of all, any of the failure modes develop naturally. We don't need to specify a range of trial surfaces in advance. And in fact, some of the limit equilibrium methods will inhibit failures. For example, we can't study toppling problems with limit equilibrium because they can't consider the internal deformations required for toppling. There really are no restrictions to geometry in numerical methods. We can look at slopes, we can look at footings, we can look at tunnels. They're all analyzed in the same way by just dialing down the strengths and looking for the point where instability arises. The numerical methods don't have any artificial parameters such as interslice force angles that have to be provided. And as I said, we can get these multiple internal surfaces that evolve naturally when the conditions are right. But I will say in my work, this particular feature pops up more than we might think. And very often we do have structures which dip back into the slope, and we can get deformation on those. Doesn't necessarily mean slopes are failing, but we end up with these obsequent scarps within the slope. And then finally, structural interaction is modeled realistically. So if we're putting in rock bolts or cable anchors or piles or whatever we want to, we can consider the interaction with the rocks appropriately, rather than looking at equivalent forces. So then let's get to the important questions. When do we use what? So which method should we use? Should it be 2D or 3D? Should it be continuum or discontinuum? I found this particular plot in a paper that I was reviewing. In the end, I think the authors pulled the the diagram, but I found it was interesting, so I'm sharing it here. On the horizontal axis, we have the complexity of the physical reality, and of course, there's no scale on this, but as things become more complex, they move to the right. And then on the vertical axes, we have the approximation to that physical reality, and it increases going upward. And then you can see the various methods on here: 2D limit equilibrium, 3D limit equilibrium, 2D shear strength reduction, and 3D shear strength reduction. And of course, when we have very simple models that are not very complex, all of our methods should give us about the same answer. But as the complexity increases and we start to use different methods, we see this divergence. Again, no scale, no particular way to use this other than conceptually. So I've put together what I consider the appropriate methods for different types of analyses, and the real objective is to try to match the method being used with the data uncertainty and the complexity as shown in the previous slide. So here are our methods: empirical, analytical, limit equilibrium, and numerical, and various stages of mine design here, all the way from conceptual to mine operations, and the data on the data certainty, and then some comments about it. So I'll just kind of go through this. Empirical methods, I think, are a really good reality check on anything we do. Just we come up with something and maybe we're looking at a slope, just make sure that it doesn't disagree with any of the empirical evidence. You're not designing slopes that have 60-degree overall angles going for 1,500 meters high, because that's not physical. But these empirical methods are very often used for closure studies, because authorities like to see how do things stack up against previous experiences. So they do get used in that way. Analytical methods, I think, are really good looking at bench and inter-ramp scale problems that are structurally controlled. And obviously bench designs are the most obvious, but some inter-ramp problems can be analyzed with analytical methods, and I think are very good for that. Limit equilibrium methods really are still widely used, but mostly they should be used, in my opinion, for things like soil and rockfill embankments and waste rock dumps and stockpiles, because the assumptions there fit the analysis method. And then numerical methods for other types of problems. 2D versus 3D, and I should say that nowadays most people are moving towards three-dimensional analysis. The software is fully capable of looking at three-dimensional models, and I just want to give you some reasons why you might want to move to 3D analyses. First of all, you shouldn't use 2D analysis if the geologic structures aren't striking parallel to the slope, or maybe the anisotropy isn't parallel to the slope. The stresses aren't either parallel or perpendicular. This is a minor point. But we have distributions very often of geomechanical units that vary along the slope, or the slope geometry really can't be analyzed in 2D, because it's changing orientations at the top versus at the bottom, and maybe the slope movements aren't perpendicular to the direction of movement. So all these things would suggest 3D analyses. A few more points about this. Certainly we can put more detail into 2D versus 3D analysis, and they're going to run faster. But what I found is not always obvious what the critical 2D sections are. You can look at them, but it's just your kind of intuition, and I've found my intuition has been wrong more often than right. As I said, the trend is toward 3D analyses. And it's kind of funny, but it's often easier just to go ahead and do a 3D analysis than explain to somebody why you did a 2D analysis. Your arguments may be perfectly valid, but people are going to question the validity of a 2D assumption. And then 3D also provide good estimates of failure volumes that are important in doing runout analyses. So the final thing then is whether we should use a continuum or discontinuum model. And you can see if I take the same structures that I have for this underground excavation and put them into a slope, the picture that you get is much different. This is one with a lot of structures in it. This one doesn't look like it has very many structures. So very often slopes can be analyzed using at least partial continuum representation. What we do most often at Itasca is try to produce a practical solution. We try to include all the major faults and as many of the other major discontinuities as possible, and this kind of depends on time and budget, and then treat the remaining material as a continuum and try to include the behavior that best approximates that continuum, which is usually some sort of strain softening model in the continuum sense. Okay, so we're almost done. Just some final thoughts. This came from a paper by Tony Starfield and Peter Kundl in 1988. It's in the International Journal of Rock Mechanics and Mining Sciences, and they tackled this question of how should numerical models be used in design analysis. They didn't highlight slope stability in particular, but rather looked at a range of problems. And their recommendations were as follows, and I think they're quite valid. First of all, be clear about what answers you're trying to answer. Don't just say, well, I'm going to run a model and see what happens, but be clear about what you're trying to discover. Try to identify likely failure modes and deformation modes, and think about experiments that might prove or disprove those hypotheses. And then use the simplest method that will allow those mechanisms to occur. And if models have limitations, perform sensitivity studies to bracket the outcome. And this is something that people in numerical modeling are quite familiar with. And then only move to complex models after you have exhausted the simpler models. One example of all this is a simple mechanism that was studied in 2011, a simple slope with a constant infiltration of water into the surface. And what happens in this is water starts to fill up and build up pressure in this vertical joint behind. And as it builds up pressure, it builds up a driving force and reduces the pressure, reduces the shear strength on the basal sliding surface, and it moves out a little bit until the water can reduce its height, and then it begins to build back up. And you can characterize the deformation in each of these episodes as shown here. So this is time in the model. on the horizontal axis and displacement. And these are progressive episodes of movement. And we can see that with each progressive episode, we get more movement. And the reason for that is that vertical tension crack gets to be bigger and bigger, and it contains more and more water. And of course, it takes longer for it to drain out, and it's acting as a driving force for a longer period of time. But this simple model and understanding this simple principle allows us to understand why slopes very often fail over time, particularly when we have rainfall. In this case, it's just a constant rainfall, but we could think about episodes of heavy rain, and we would see the same trend, but it would be exaggerated, that every time we get movement, we tend to get a little bit more movement, and eventually this slope is going to fail. So that's what I wanted to talk about, and a lot of material there. As David said, we'll upload this presentation that you can look at and also listen to the recording. But maybe we can take some questions. I've got some time now, and we'll see how we go.
Okay, great. Thank you very much, Loren. So we do have a couple questions. One you just answered. So the presentations themselves will be uploaded, and the recording of this webinar will also be uploaded to our website within the week. At the end of the webinar, or shortly after it, anybody who registered receive an email which will include a link to the web page where you'll eventually be able to find the recording and the webinar as a slide set. In terms of specific questions, the first one, Loren, is referring to slide 19, and they're wondering if that angle is referring to the inter-ramp angle, the IRA.
So it could be. There's no designation if this is the slide that we're talking about. These were simply slopes that were collected at the time, and they very well may be just inter-ramp slopes, and that might explain partially why they are limited in height. But I think also some of these are overall slopes. Certainly, slope heights have increased over time. We know that, but I don't know. I haven't looked at the database to know whether these are all inter-ramp or some of them are overall. I suspect it's a mix.
Okay, thank you. The next question is, how do flow rules affect the factor of safety?
Okay, yeah, very good. So by flow rules, we're talking about really dilation, and how when we get plastic failure, how do the associated deformations occur, and that's really relates to dilation of the failed material. And associated flow rules are those where the dilation angle is equal to the friction angle. So those are really physically unrealistic, or very seldom do we have materials, or in fact, I don't know of any materials where the friction angle and the dilation angle are the same. Typically, the dilation angle is something less than the friction angle. And then the question is, well, how important is that dilation in the analyses? The analytic solutions for slope stability, if you look at them, they're all based, not the block sliding or the wedges or the planar or the toppling, but the sort of rock mass failure modes. The analytic solutions for those all assume an associated flow rule because it's the only way they can be solved in terms of an analytic solution. So they have friction angle equal to dilation. And that's not physically realistic, as I said before. But the differences when you use dilation or not are small. The place where this becomes an issue or can become an issue is where we have these internal deformations. There it becomes a little bit more important. So in this particular case, where we have internal deformations, to try to capture that dilation, because if we assume it's zero, for example, which is perfectly fine, but it's conservative, because most materials do have some dilation, except for maybe clay. And internal deformations then would be affected by dilation. So, we try to figure out what that is. It's not usually something that makes a difference of more than a couple decimal places in a safety factor. But I think it is important to include some dilation rather than making it zero. And our models, particularly the IMAS model, has all an evolution of the dilation because it's not a constant value either. It does depend on how the rock mass is breaking up. But in general, the flow rule doesn't have a huge effect. The dilation doesn't have a huge effect, but it doesn't cost you anything extra to put in, say, 5 or 10 degrees and see what happens and see if there's any difference.
Okay. Could you address the conversations taking place regarding the difference in strength properties between 2D and 3D models? Should they be the same? Why or why not?
Yeah. Okay. That's another good point. So, in my way of thinking, strength properties are strength properties. We don't have good tools for estimating strength properties. We rely almost exclusively on empirical relations, and then they get used in different models, 2D or 3D. What we find is that if you calibrate something in 2D and you apply it in 3D, those properties don't give kind of sensible answers. And the reason comes down to the assumptions in the 2D model that you have an infinite slope, which is not physically realistic. So, that if you want to calibrate things in 2D and then just continue to use them in 3D, don't try and go ahead and use them in 3D or vice versa, because you're going to run into problems there. And I think rather than the properties being different, it's really the assumptions about the kind of the slope and the slope geometry that are important. And I think this is another reason why people are moving away from 2D models, is because they don't represent physical reality.
Okay. Do you have any comments on strength criteria used in numerical models, i.e. the different ones out there and the shortcomings of some of them, specifically when considering the stress relaxation of the disturbance that should be considered in the Hook-Brown approach?
Yeah. So, I wanted to stay away from that because, so this is this first bullet point up here that I said I wasn't going to talk about, but I'm happy to talk about it. Look, the Hook-Brown failure criteria obviously is and has been useful in a lot of applications, and it has been used successfully in a variety of slopes. But we do run into problems when we apply this D factor because it just is not well defined in, first of all, what it does and where it should be applied. The first point is, let's talk about what it does. What the D factor does is it reduces the friction and the cohesion of the rock mass. Now, people have looked at this and most people have concluded that, yeah, the cohesion certainly drops, but the friction angle really doesn't. In fact, the friction angle at low confinement, which is what we're most concerned about in slopes, can actually increase. And there are papers that demonstrate that. So first of all, the first point is that what the D factor does doesn't agree 100% with reality. And by the way, I've corresponded with Everett Hook on exactly these points that I'm going to mention to you. And I've written a paper together with some other people that appeared in one of the Australian slope stability conferences that talked about this, and we studied it in the LOP quite a bit. And so this concept of frictional weakening due to damage is probably not, in most cases, appropriate. And then we have the whole issue about, well, what the D factor should be, where should it be applied, even if you want to accept that first premise. And early work from Everett suggests that it should be applied only to blasting, and even some of his later work, most recent, he's again trying to tackle this and saying, well, it should only be applied to blast damage. But we know that there is damage due to stress relaxation that occurs. And it extends deeper than than just what you would get from looking at blasts. So the other evidence that we have, and probably the biggest evidence that we have about what's the right way to go about this, comes from looking at failures. And when you look at failures of slopes, the first thing you see is that by and large, they're fairly shallow. They very seldom exceed 100 meters, even in the biggest slopes, and most often they're less than 50 meters. So what does that tell us? It tells us that, first of all, these failures are probably largely frictional, and this is in the area where normal stresses are most important because they change. Once you get to depths, beyond 50, 75, 100 meters, there's just too much confinement for rock masses to fail, so they don't fail at those kinds of depths. If you use the Hook-Brown approach of D, where the friction angle is reduced, then you end up with deeper failure surfaces that don't necessarily agree with reality. And so one of the things you should do, I think, in any analysis, and particularly when you're looking at shear strength reduction or factors of safety, is look at what the potential failure surface is. And if it's very, very deep, you should challenge your assumptions there, because deep failures just don't happen in reality. And we see that when we apply the D factor. We also see it, by the way, in 2D analyses, because 2D analyses tend to be very deep, particularly with large safety factors, and those things probably are just not realistic. But we get shallower failure surfaces in 3D analyses, and when the material, the rock mass material, is more frictionally dominant than cohesionally dominant. All these things, by the way, are great questions without real solid answers, at least on my part. We're continuing to look at these things and research them and try to understand it and look for data that supports these various hypotheses.
Okay. Do you have any comments or suggestions for analysis with interaction of rock and soil, such as regolith, typical expected behavior, support method, etc.?
Not really. I think it's just a matter of particularly on the soil part. I'm not an expert in soils, but there are n number of constitutive relations for soil, just as there are for rock, and the trick really is to use the constitutive relation or the material model, which you have support for in terms of testing or experience or anything else. Use that particular model where it's appropriate. So soil models for the soil part, and rock models for the rock part. And you can do that with almost any numerical model, whether it's Itasca's or Rock Sciences or anybody else's. They have a variety of material models, and just use those where they're appropriate.
Okay. What is the best way to model faults from input material to numerical modeling?
Say it again, David.
What is the best way to model faults from input material to numerical modeling?
Yeah, again, so before I say that, I'll say that the most important part of slope stability analysis is identifying the weakest components, and that may be a fault, it may be a bedding plane, it may be a rock mass, but that's where we need to spend our effort. And rather than testing, rock which has 200 megapascals UCS and figuring out what its modulus is and its Poisson's ratio, we do need to spend our time and efforts looking for and characterizing the weakest parts. And these are very often faults, and very often they get ignored by people in the field, by people building models and so on. But because they are weak components, we must include them in our models in the best way possible. And two fundamentally different approaches. They can be modeled as explicit interfaces in something like FLAC 3D. Or 3DEX. So these are surfaces which have no thickness, but they can have slip and separation. And that's probably the way to best represent most faults. But some faults are really fault zones. They have a thickness to them that may be 5, 10, 15, 20 meters thick. And there we might want to include them more as a material model. So it's just a matter of kind of looking at the geometry of the fault or fault zone and deciding, what kind of model to use. But then it comes the question of properties and how do we go about getting the properties. And this really goes back to soil mechanics and because very often the material that's in these faults is more soil-like than rock-like, and using some appropriate methods to try to get those strengths. And if it's clay, get some clay samples, at least do some Atterberg limits and get the plasticity index so we can estimate the friction. And just good photographs, good basic characterization, how much rock, how much soil, how thick is it. One of the things that we've been trying to push people to use is not a pocket penetrometer, but a needle penetrometer, because needle penetrometers are capable of estimating strengths for fault-like materials. It's a fairly cheap instrument, but seems to give pretty good answers. And I know John Fedorovich in Canada is a big proponent of using these needle penetrometers, and we've worked with him, and he's used that particular tool to provide at least reasonably sounding strength parameters for faults. So not an easy question, but a place where we need to spend time and effort to try and estimate the properties and get them into the models as best we can, because they are a weak component.
Okay. I know you have to run at 10, Loren, but we have a couple more questions. I'm sorry,
Okay.
at 11, I should say. There was a question about the NPM animation.
Oh yeah.
Has the new model that predicts runoff being calibrated or back and analyzed?
Not to my knowledge.
Right.
It's still early days on this.
Yeah, I would just add is I think that's just an illustration almost more of the potential and the actual methodology, the math and the physics that goes in behind it is still being developed. So it's very early days before this will be, I think, used for consulting or sold as a commercial product.
Yeah.
And then you mentioned explicit inclusion of joints in 3D modeling using 3DEC. Oh.
Yeah.
How would you account for strength anisotropy at a smaller scale with intact rock for a large scale model?
Right. So when that question comes up, what we've tried to do is do analysis with what's called synthetic rock mass. So you make a sample which you hope is representative of a portion of the slope. Typically we might pull out a cube of material which is 15 meters on a side, try to put in all of the components, the joints into that, and then test it and derive the anisotropic strength, and then put that back into a model which accounts for the anisotropic strength in some way. That's probably the best approach. We don't always do it because the synthetic rock masses take some time. Maybe we don't have all the information available, but that's, given time and budget, that's the way to do it.
Great. And then the last question, is there any information about shear stiffnesses and normal stiffnesses used in PFC examples?
Whoa, I don't know about that. I know that there are calibration tools available. So if we know, for example, the rock mass modulus, it will provide the at least starting stiffnesses for those. But I'm not really a good one to ask about that because I don't do anything with PFC. But I do know that at least there used to be some tools available to at least give you the right stiffness that will produce the right modulus of the sample. But there's probably way more guidance available than I'm aware of.
Okay. And I can send the person who asked that question a couple of links to the website where I think some of those tools exist, that sort of our material testing functions to help you do essentially virtual lab experiments. And then, like you say, it's sort of a calibration process to go from a micro to a macro strength or stiffnesses. Okay, well, that is the end of the question. So Loren, thank you very much for all your time presenting and answering questions. Thank you to everybody who joined us today. Again, you should receive an email with a link to the webpage where you'll be able to watch the video from today's presentation and download the slides as a PDF. And that should be out within a week. So look for that email. Thank you, everybody, and have a good day.